second page. Second page where we were somewhere in the middle, but I like to go through the page, just refresh your memory. Yeah. All right. So here, we need to develop a formula for non-homogeneous linear ODE, first order. Yeah. Here, this module, we're working on first order ODE. Yeah. So the general form, we are working on that one. Okay, general form. All right. So because we want to use that, what's that? Extended exact form. Yeah. We need to find integrating factor. Yeah. So we write it as a standard form for the differential form, standard form. Okay. After that, there are two options for us to select integrating factors. Yeah. So first, this one is the standard form. All right. Our current form, we write here, so we do comparison. Yeah. What's the difference? So we can see the difference clearly. Next, our two options. First option, f is a function of x variable, a single variable function. So, yeah, so in that, this case, so we need to have this equality. Second option, yeah, this equation, yeah. But these two options for our current equation, our current equation is very special. So what we want to see for this special equation, which option is better? Yeah. We want to choose the one that is better. Okay? Yeah. So how do we determine which option is better? We look at the criteria, because in order to make our current equation exact after we multiply the f integrating factor, certain to be determined f, we need this condition. Yeah. To make this possible, yeah, because sometimes you may not get it, right? Impossible. In order to make this equality possible, let's look at the second option. Because f is a function of y variable. There is no x involved, only y. Yeah. This capital N corresponds to f times q. F times q, that's the capital N. But our q is 1. So f times q, that is f. F is a function of y. So n is a function of y. Yeah. So here we can safely, yeah, yeah, all right. Yeah, let me change the color. Yeah. So this n equals f of y, all right? Partial m over partial x, that's 0, right? 0. Then, last time I said too restrictive, because you want partial m over partial y equals 0, although it could be possible, but too restrictive. Yeah. To make it happen, you need to sacrifice a lot. Okay? Most of the time, it's impossible. Yeah. So we don't want to take that option that narrow our chance greatly. Okay? Our chance would be greatly reduced. What is the chance? Our chance to find appropriate integrating factor f would be greatly reduced if we choose the second option. So for that reason, we drop the second option and we take the first option, because our chance would be much larger to get a good integrating factor f. Yeah, okay. This part not explained in the textbook, so I spend a little more time explaining here. All right, next, after we make our decision, select f as a univariate function of x. Next, we can simplify our equation, because we can further simplify. Yeah. This one, this is the, the equation from the standard form, right? The general standard form. Yeah. But for our particular equation, we can do further simplification. So we do another round simplification. Yeah. So this round, because q is 1, q partial x, partial q over partial x, that's 0. Yeah. So this term is gone. So we can make our differential equation as simple as this. Yeah. So simple, so we can solve it easily. Yeah. So next, let's solve it. Yeah. But before we solve it, before we solve it, f is a function of x. F prime also a function of x. F prime over f, left-hand side, function of x. So right-hand side, p, look at the special p we have. That's the special p we have. So we can do the partial p over partial y, because the second term gone, becomes 0, second term. First term, we treat x par constant. So partial y is gone, all right? So that is just exactly the p. So it's a function of x. It tells us this f can be found explicitly. No, with this equation. Yeah. So let's write the separable form. Take integral, both sides, absolute value of f. And this whole function, we define it as, introduce a new symbol notation, h function. So this colon means the definition. Okay, yeah, definition. So we make this integral expression because we want to make our later expression simpler. So we introduce this notation. Otherwise, our later expression could be very complicated. Yeah. So h, we let h be this whole integral function. Yeah. Next, because we want to get f, there is absolute value in f. So the question, how do we deal with that absolute sign? Yeah. Because it's quite annoying. If we keep the absolute value sign there, when we do operations, it could be very hard. So we want to get rid of the absolute value sign. The question is, we need to justify it. When we get rid of absolute value sign, we need to justify it. Yeah. But here, think about, our goal is to find an integrating factor. We only need one particular integrating factor, right? So we do not try to find all possible integrating factors, right? Yeah. So we only need to pick one among a large pool. Yeah. There are many functions that can be used as integrating factor. We only pick a special one. So when we have freedom to choose a special one, we choose one without absolute value, right? We choose this special function. Yeah. So when you look at absolute value, you want to see, do we want to write the general solution? If the general solution, then you need to make sure you handle absolute value covering all the cases. Okay? If you only need one, then you don't worry about other cases. You just get one of the cases. Here we only need one. So we don't worry about the general cases. Yeah. So it's safe for us to get rid of absolute value. Only one special case. Yeah. Later we have several situations like this. Yeah. All right. Now after we multiply the integrating factor, next, remember the n function, we apply formula. Yeah. So you always need to, get back to the formula. Yeah. So when you work, find the formula. All right. Yeah. To do integral, n function, we know it's that. So let me compute integral of m here. Yeah. So I want to explain the details. Yeah. All right. So this is the definition of m function. Next step, we want to, so let's write it in a simpler way. Yeah. P function, let's skip x part. Make it as simple as possible. We know it's a function of x. P times y minus r. Yeah. Make it, more compact. Yeah. Then, let me write this form in another way. Here, I like to, make sure you can understand this step. Can we replace P by H prime? Remember the definition of H here. H is the integral of P. Can we, when we take H derivative, we get a P from this definition? Can you see that? Everyone feel all right? Okay, yeah, so that's good. Yeah, so integral derivative, inverse, right? Inverse operations. Yeah, so we take H prime, P, we treat it as H prime. Yeah. While we write this way, later you will see when we do the integral, we need this structure. We need this structure. Okay? All right. Now, integral on m function, there are two terms. So let's split. Integral on the first term, integral on the second term. Second term, just write it out. We do not do anything. We just write it out. Okay? But can you see integral on the first term, we get a y times e to the h? This is a little harder to see it. Okay? A little harder to see it. Yeah, let me write a little more detail here. Yeah. So, because this first integration, you need to use that h prime version. You need to use that h prime version. So let me write right here. Okay? Yeah. So we want to do integral py dx, right? Yeah. All right. Y we can take out, right? Yeah. Y, because it's nothing to do with x here, so y we can take out. P, we can write h prime, right? So e to the h dx, right? Yeah. Now, y, this step, can we write this h prime inside the differential d? That's the step I like you to, get familiar with. Feel comfortable. Yeah. Put h inside the differential operator. So we write e to the h dh. Can you see that? This step. Yeah. Because here there is a derivative. This is a differential operator. We can put this inside derivative, remove that derivative. Yeah. Remember, dh equals, here, let me write it clearly. Yeah. dh equals h prime times dx. I use this equality here. Okay? That's the relationship between differential and the derivative. This is the relationship. Okay? That is the relationship. dh equals h prime times dx. Here, we use this equality in a reverse way. Okay? Reverse way. We have the right-hand side. We write it as the left-hand side. Okay? Yeah. From right-hand side to left-hand side. So after we get this one, then we can write y e h. Okay? So that is the first term here. Okay? That's how we get the first term. First term. Okay? Yeah. Here. All right. Derivative differential, I use that step. Yeah. Yeah. We frequently use that property. Okay? Yeah, we frequently use that property. Yeah. So you need to get used to it. Yeah. All right. Next. Yeah. All right. So I hope if you write it down, because I need to erase this part. Yeah. I have something display this place later. Yeah. My final solution I need to display here. So I will remove these things. Yeah. All right. Yeah. Then we can write the expression clearly like this. Yeah. That's the first version, because we have a second version based on n function. Yeah. N function, because n function much easier, right? N function, yeah, this is n function, all right? This n function much easier. Integral with respect to y. This whole e function, e to the h, only contains x, no y. No y. So the integral just y times e to the h plus L function. Okay? So the last step, write the whole u function out. Remember last time I recommend a shortcut, a faster, simple way to get a u function. You just write all the terms that appear in these two expressions, but the same, you only write once. Right? Yeah. So you write the union, okay? Union of the terms from two expressions. Yeah. Union of sets. Yeah. Use that concept. Union of two sets concept. All right? So the first term, you keep it. And the second, yeah. Then right hand side you use constant little c. Constant little c. Yeah. Yeah. To write the final solution, because our final solution we like to write y equals a function of x. Why? So here we need to do division both sides by this e to the h function. So we get a y expression out. Yeah. To do division. Yeah. So the final solution after we do that division, y equals this expression, c. Okay, two terms. Yeah. Negative to the h. H, then we put it aside. Yeah. So let me erase this. Yeah, H. So we calculate H out first. Then we use H in this Y formula. That's the solution formula. Okay? That's the solution formula. Yeah. So here, after you understand the derivation of the whole formula, so I hope you get good impression because you understand the development process. Later, when you use it, I hope you use the formula in the right way. Yeah. When you understand better, so you can use the formulas in the right way. Yeah. Because we have so many formulas. Yeah. I'm afraid you may use the wrong formula, right? Yeah. Use the correct formula. Yeah. All right. So we finish that part. Next, solve linear first by formulas. Yeah. So now we have the formula. We just apply the formula to find the solution. Yeah. Here I give you that example. Yeah. So you can see P of x tangent x, Q R of x, not Q. Yeah, R of x, sine of 2x, then initial condition. Yeah. Plug in the formula. That's simple. Okay? Yeah. Then the calculation. We need to be careful in the calculation here. Right? Yeah. Solution. Formula to be used. Y prime, yeah. So that's the general form. So I just put there for comparison. Okay? Yeah. Because our formula, we write it on the general form. Yeah. Here, P of x equals tangent x, R of x equals sine of 2x. So the solution formula from the previous slide, y equals this expression, but h, we need to find its formula integral first. Yeah. Now, let's just do the work. Yeah. All right. Let's calculate h first. Yeah. Integral of tangent x. Yeah. Now, check your basics. Check your integral formula, basics. Yeah. Tangent. Can you see? We can write this. Tangent equals sine x over cosine x, right? Sine x. Can you put sine x inside that d? Sine x is the derivative of cosine, but there is a negative sign. Derivative of cosine equals negative sine x, right? Yeah. Basic formula. Derivative of cosine equals negative sine. So we have this negative sign. Okay? Yeah. D cosine x, that's the sine x times dx, but there is a negative sign. Yeah. That formula I mentioned in the previous slide, that h dh equals h prime, yeah, exactly that one. Here, the same thing. Yeah. Same thing. Yeah. 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 All right. Hope you get used to it. So later, so you will feel comfortable doing things like this. Because inside D and this bottom function the same, natural log, right? We have that formula. Yeah. Why are we writing this way? Because we want to apply that natural log formula. That's the reason. Yeah. Equals natural log absolute value of cosine. Okay? Yeah, here absolute value again. All right? Yeah. So we need to be careful because here we try to find all the solutions. Yeah, so we need to, work it in the right way. Yeah. Can you see this negative log natural ln of absolute value cosine? I put this negative as to the exponent position, I get secant x. Can you see that? Secant x. Secant x is 1 over cosine x, right? By definition. Secant. Secant x is 1 over cosine x. So this negative sign, I put it to the exponent of cosine x, so it becomes secant x. Why I do that? Yeah, here. Why I do that? Yeah. So here I have two expressions. The first one without with negative sign, second one without negative sign. Later you will see. Oh, question. Numerator what? Substitution for the numerator. Do you mean this step?
So right before that step, where sine of x over cosine of x?
Yeah. Yeah, you can use substitution. Yeah. You can use substitution. Yeah. So here I'm talking about, some faster way, shortcut way. Yeah. Substitution, you need to get there and get back, right? Yeah. So at early stage, you can do that a few times. But when you becomes better and better, you can skip that substitution step. Okay? So here, yeah. After you practice a few times, when you feel comfortable, you can skip simple substitution. For hard substitution, then it's hard to skip, right? Yeah. But simple substitution, yeah, so we can handle, so we can skip. Yeah. So that's the point. Yeah. Yeah. All right. So now we are here. So you may ask me, we have this expression, why you want to put that negative sign there to get a secant x? Because most people may not be familiar with the secant x, right? People are familiar with sine, cosine. And many people may not be familiar with secant, cosecant, right? Secant, cosecant, yeah. So here the reason is, in the next few steps, sometimes the first version is better, sometimes second version is better. You will see. Yeah. When we are in the situation that first version is more friendly, we use the first version. When we are in the situation the second version more friendly, we will use the second version, right? So here we have two versions. So we have freedom to choose which one more convenient to use in our following calculation. Yeah, so I will show you. Next. Now, our y formula, yeah, here, this one, yeah. Here the constant, I use that C star, yeah, because later there is a, constant change. Yeah. Later, we need to do some constant change. So here, the temporary constant, I use that C star. So the final constant, I use C. Okay? Yeah. All right. That's not important. If you use C, that's fine. Yeah. That's fine. Okay? So here I use C star. Yeah. All right. Now, H function. Here, we need to plug in H function, right? Yeah. H function, we have all the two versions. When we plug in H function, we like to choose which one more convenient to use. Yeah. All right. In this first one, this first place, we want to plug in our H function. Which one you feel better? The first version, second version, which one you feel better? Which one?
First version.
Good. Why first version better?
Because the two negative signs.
Right. Correct. Yeah. Because after we cancel out the negative sign, you will see the following formula. There is a following formula. The following formula rely on that. Otherwise, the following formula, it's very easy to get a wrong result. Yeah. So here, canceling that negative sign, very useful for our following calculation. Yeah. All right. So here, the first version. Then this one inside the integral, there is no negative sign. Which version you like to use? The one inside integral. Yeah, there is no negative sign. So second version is better, right? Because we want to avoid negative sign. We want to avoid negative sign. Okay? All right, here. So we use the secant version. See? Yeah, secant version. Now let me explain why get rid of negative sign in this particular situation is important. Is important. Okay? Yeah. So let me write this formula. And you tell me if you are familiar with this. E to the natural log of x equals x. Are you familiar with this formula? So, good. Yeah, that's good. Because the same base, natural log of e base. There, your exponential function also use e. Log, so like cancel out. Only you keep that x. All right. But think about it. If you put a negative sign in front of natural log, then you may apply the formula in the wrong way. Okay? If you put a negative sign, first you cannot use the formula directly. Some students, if you use negative x, it's wrong. Okay? So I'm afraid if you keep that negative sign in front of natural log, you may write answer negative x. Then you get a wrong answer. Because e function, how can e function get a negative number, right? E to any number is positive, right? E to a real number. Here I do not say complex number. E to complex number could be negative, okay? So here we're talking about e to a real number. Can never be negative, even 0. Can only be positive. But if you put a negative x, you are wrong. Okay? So here, we do not want to leave negative x in front of it because we want avoid people put a negative sign here. Okay? If you do not see negative sign, then you won't apply the formula wrong, right? Yeah? You won't apply the formula wrong. So here, when you see this no negative sign, this whole thing, you just write absolute value of cosine x. Okay? So here, no negative sign, you just write this absolute value of secant x. Okay? Yeah. 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 All right. So we have that. Yeah. Oh yeah. Everywhere. Yeah. Absolute value. We keep that. Yeah. All right. Then, because absolute value, we want to, really see if we can simplify it. Yeah. Absolute value is still quite annoying. Yeah. So we want to simplify it. Make it look, more friendly. Yeah. Not that messy. All right? Yeah. So we have two cases, right? So this formula we consider the first case when cosine x greater or equal to 0, we can write one formula. For the second case, when the cosine x less than 0, we can write another. All right. Now, let's write the final formula. Yeah, final formula. Now, first, absolute sign gone. Yeah, but our final formula, look at each one. The first one, the integral, after integral on x, sine x, we get cosine, right? Cosine, but there is a constant, right? Because this indefinite integral, there is constant carried with the result, right? Don't forget that constant, okay? Some constant times 2x, that constant times some constant, add to this C star constant, yeah? How about we just use a new constant to represent it? 2 times certain constant plus C star constant. How about we treat the whole thing as a constant, one constant? Yeah? Whole thing as one constant. So we do not write that many constant thing. Yeah. So the whole thing we use one little c constant. Okay? So you know, there is constant comes out from the first integral, 2 times that constant. And you need to add to the C star constant. Those constant terms, we just call it C constant. Okay? Yeah. So the remaining non-constant part. Yeah. So both cases, just the way to write that constant is different, right? 2 times some constant, this time minus C star, we can also treat it as a constant, right? Yeah. Because this constancy is arbitrary. It's arbitrary. Arbitrary, we can choose, all different constant. So we combine the 2 cases. After we use the constant flexibility, so we can combine 2 different cases. So we want to write one, here, we only need to write one formula, one clean formula. Okay? Yeah? Yeah. So then, this little c, we can use the initial condition to determine. Okay? Yeah. Plug in x and y of 0 equals 1 equals c cosine 0 is 1. All right? Yeah. Cosine 0 is 1. So c minus 2. So c equals 3. Yeah. So we can write the final solution 3 cosine x minus 2 cosine square of x. Yeah. So that all the details. Yeah. So in computation, so you can see we need to do many very special treatment, so many steps. The sign treatment, reciprocal, all those places. Yeah. Yeah. It's not easy, yeah, but I hope you can follow. Yeah. Yeah. Later you need to do the same thing. Yeah. All right? Yeah. Let's move to next topic. Oh, yeah. I didn't do the animation. Oh. Yeah. All right. Let me save some time. Yeah. So, yeah. First, let me give you the question. The hormone level. Yeah. Assume that the level of a certain hormone in the blood of a patient varies with time. Yeah. Suppose that the time rate of change is the difference between a sinusoidal input of a 24-hour period from the thyroid gland and a continuous removal rate proportional to the level present. Set up a model for the hormone level in the blood and find its general solution. Yeah. Find a particular solution satisfying a suitable initial condition. Yeah. Here, this one. Yeah. Here, I only, first set up the model. Then, yeah, because this one, if we use symbol, the computation could be very complicated. Yeah. All right. So here, first, let's understand the question. We want to calculate the hormone level, y of t, the hormone level at time t. Yeah. But the main rule is given in the question. The main rule we can use is given in the question. Yeah. So what's that? Starting here, suppose that that's the rule we need to apply to set up equation. Okay, the time rate of change y prime, right? change of what? Hormone level, okay? Time rate of change of the hormone level. So that's the y prime expression. All right. Equals right-hand side, difference. Okay? Difference. The first term in that difference, right-hand side, between sinusoidal input. Yeah. Input is a sine-like function. Yeah. Sinusoidal, yeah. Sine-like. Okay? Yeah. That curve, that sine curve. Yeah. And here, sinusoidal input, here we use this A plus B cosine. Yeah. Sine cosine is the same shape, right? Yeah. Sine cosine is the same shape, just the phase different. Phase different. Okay? But phase we can adjust, right? Yeah. So here, yeah, some people like to use the cosine. Yeah. Cosine, there is a good thing about cosine. At 0, cosine is 1, right? That's convenient. So when you do initial condition, at 0, t equals 0, cosine value is 1. Yeah? Yeah, so that's the reason many people like to use cosine. Yeah. For sinusoidal, still cosine, yeah, for convenience. Okay? But the shape the same. Yeah. Shape the same. Yeah. A, B to be determined, two constant to be determined. Okay? All right. So that's the first term in that difference. The second term, all right, 24-hour period. Period 24 hour. Yeah, we need to use it to determine the omega. What is the omega? Omega used to determine the period. Periodic function. Cosine, we know cosine is a 2 pi periodic function, right? 2 pi. Yeah. But here, the period is 24 hours. So we need to adjust the cosine function from the original period 2 pi to 24 hours. How do you adjust? We use this omega to help us adjust the period. Omega, yeah, that parameter we can adjust the period, real period. Yeah. All right. From the second term in the difference, thyroid gland and a continued removal rate. Yeah. Oh, so that's the first part. Okay. Yeah. From that gland. Second part, a continuous removal rate. Yeah. Removal rate. Yeah. Minus losing. Yeah. Removal. Yeah. Hormone level reduced. Removal rate. Okay. Minus something, removal rate. That removal rate is proportional to the level present. What's that? Level present. Presence is y of t, removal rate k times y of t. That's the removal rate. Yeah. Second term, removal rate. Yeah. All right. Then, here I calculate the omega. I need to calculate the omega. All right? Yeah. So here, we know, so I do the calculation here. All right, I do the calculation. Yeah. The first one, the relationship between sine function, cosine function, a difference in this phase, this angle, pi over 2 angle. Okay? Yeah, pi over 2 angle. You just change the angle by 90 degrees, pi over 2. You change from sine to cosine. Yeah. All right. So that's the first one. Second, we want to calculate the period, the periodic function. All right. All right. We know cosine function has 2 pi period. Omega t plus 2 pi. Cosine of this one equals the cosine omega t. Yeah. So here, after we take omega out. Inside the parenthesis, we get a t plus 2 pi over t, over omega, all right? 2 pi over omega. And then this is the new period, t plus a new constant. This is the new period after we factor omega out. New period number. So this new period number, based on the question, it's 24 hours. So we have this 2 pi over omega equals 24 hours. 24 hours, all right? So then we find omega equals pi over 12. Yeah. So then we go back to the, this input, sinusoidal input. So by Balance law, I'll talk about Balance law later. Yeah. Y prime equals input sinusoidal input minus removal rate k times y. So this is the final equation. Final equation. Yeah. Here, why I use this Balance law? Remember, we used the Balance law before, right? Yeah. Think about. Actually, at several places. Yeah. But one place. Remember that tank. Yeah. Mixture in the tank. Remember that mixture in the tank. Okay. So you have the, y prime, the amount of salt, rate of change of the salt, equals the rate, inflow rate, right? Inflow rate minus outflow rate. Can you see the similarity, our situation here? The hormone level, okay? Just like the, amount of salt in the tank. Yeah? The rate of change, the rate of change of the hormone level. Then inflow, sinusoidal input, we treat as the inflow. How about that? Okay? Removal rate, we treat as outflow. How about that? Okay? So we see the similarity. So here I refer to the Balance law. All right? Balance law. Because this situation could be repeated in many different questions with same pattern, with same pattern, but different content. Different content. Okay? Yeah. So later, because after you use the Balance law to look at this kind of relationship, then you feel more comfortable, so you can set up equations faster. Because you're familiar with, all those kind of things. Yeah. All right. Yeah, so here I refer to that Balance, our old Balance law. Y prime salt inflow rate minus salt outflow rate. Yeah. So look at the similarity here. We have the same pattern. Because when you talk about Balance law, it's very general, right? In the real world, it's very general. Why we have to be restricted the Balance law on the tank salt stuff, right? Why we cannot apply it on the general things, right? Yeah. So it's not necessarily only you can apply on mixture, salt, tank, that kind of questions. Yeah. You can apply it to a large class of questions. Yeah. All right. Another comment I like to make here is, because here there are so many constants, A constant, B constant, K constant. So the solution, so I do not do here, the whole solution you can see in the textbook, but the solution is very complicated. So I'm afraid it's very hard to follow for you. So if I make questions, I like to choose suitable constant. So I try to figure out, so which constant can give you some good formula, good looking formula. So then I will use. If it's some nasty formula, so then I won't give you that kind of questions. Too nasty. So you can look at the formula on the textbook. Very messy. So that's why I do not put here. Yeah, otherwise you will get scared. Yeah, yeah. Because I do not like to see myself. Yeah, I feel hard to see. Yeah, things clearly. Yeah. All right. So we finish this topic. Yeah. Yeah. All right. Yeah. Yeah. I will fix. Yeah. All right. Okay. Next topic, Bernoulli equation. Yeah. Bernoulli equation. Yeah. So another special type of first order linear differential equation. Yeah. Reduction to linear form. Bernoulli equation, by its definition, it is not a linear equation. It's not a linear ODE, nonlinear. All right, because it has very special structure, so we can convert it to linear form easily. So that's why, so we take it out. Yeah. But this Bernoulli equation, because it can be used in several application, real-world application questions. So it is useful. So we study this special equation. Yeah. Bernoulli equation, you can see the right-hand side, there is a term, g of x times y to the a. There is this parameter a at the exponent. This term calls the nonlinear property in this equation. Okay? Yeah. A is any real number. Any real number. Yeah. All right. Here, let's discuss a few cases of Bernoulli equations. First, when a equals 0, so you can see when a equals 0, then we just go back to the non-homogeneous linear form. Yeah. We just studied. We have formula for it. Non-homogeneous. Yeah. All right. Yeah. Y prime equals. Yeah. So we have the formula. But when a equals 1, now you can see we get a homogeneous equation. Also easy. We can solve it easily. Homogeneous. Yeah. So you can see here we should consider a should be a value other than 0 and 1. Then we need to find a solution. Yeah. These two cases, we already have the solutions. Yeah. All right. So now, let's work on the, general case. Yeah. General case. Yeah. This general case, the substitution is important. After the substitution, we get to a linear form quickly. Yeah. That magic. Okay. Yeah, that magic. All right. So this substitution is u function equals y function to 1 minus a. That special substitution. Okay? Yeah. That substitution is special. You may ask why, just some mathematician found it. Okay? Someone, was lucky and found this one. Then every other people just use the same substitution, right? Yeah. Yeah. All right. Derivative by chain rule here. Let's calculate u prime by chain rule equals 1 minus a parenthesis times y to the negative a times y prime. Yeah. So let us put it back to, because we want to write a y prime expression. Y prime equals y to the a times u prime over 1 minus a. Put it back to the original equation. Yeah. You can see, yeah, after some simplification, we get a differential equation, linear first order differential equation for u. For u. Now, we have the formula for this type of ODE. Yeah? That type of formula, so we just derived before, we had a formula. Okay? Yeah. The H function, remember, calculate the H function first, then we can write the Y solution immediately. Yeah? That previous formula. Yeah? We treat, yeah, so at this point, we solve it. We solve it. Okay? Yeah. Yeah. So that's the Bernoulli equation. Yeah. All right. All right. Yeah. So here we treat, we have the solution. Yeah. But when you solve the Bernoulli equation problem question, after you get this point, you need to go back to find the right formula to apply to complete the solution. Yeah. Complete the solution. Yeah. All right? Yeah. Yeah. All right. Then, next, logistic equation, a special case of Bernoulli equation. Logistic. What's the logistic equation? Yeah. A French mathematician, studies some special type of questions and derived this type of equation. Y prime equals A constant times Y minus B constant times Y squared. So he called it logistic equation. Yeah. First, this one is not a linear first order, not because Y squared. Okay? But it's a Bernoulli equation, right? A equals 2. The Bernoulli, A equals 2, so we can do some substitution to make it a linear first order equation, so we can apply formula. Okay? Yeah. Here, this logistic. Yeah. So I search. So I try to see why it is called a logistic. Yeah. Based on the Wikipedia explanation, yeah. It has nothing to do with our usual understanding of logistic. Okay? Yeah. Because the word comes from the French. The meaning is different from English. Yeah. So it's not our English logistic. Yeah. It's a French logistic. Yeah. All right. All right. Yeah. So for two non-zero constant. Yeah. Solution here, let's do substitution. Yeah. After the substitution, yeah, so we need to, put it back to the original equation. We get U prime plus AU equals B. Yeah. This equation is so easy to solve, right? Yeah. So easy to solve. Yeah. Yeah. So we can apply the formula. Yeah. Here, although we can do the calculation, H, because P is A, AT. All right. We can write U from H formula directly. Yeah. Yeah. And then, yeah, so simplify a little bit. Yeah. Yeah, because we can find the integral easily, right? So cancel out. Yeah. Then the final solution, Y equals this one. Yeah. Yeah. And or you can write it in different form. Yeah. So that's logistic equation. Yeah. All right. So let me pause here to give you a break. Yeah. After you come back, we just have last slide talk about the population model, population growth. Yeah. Last slide. So we finish part D and module 1. Yeah. So then we can start module 2. Yeah. All right. Yeah. Break time. Yeah.